Now we're going to use some of our knowledge of graphing functions and finding extrema and some applications. 4.6 is applied optimization, and the plan is to find local and absolute extrema of functions in various applications. So there's nothing new technique-wise in this section, so we'll largely just run through a bunch of examples, some fairly involved. So first, let's just look at an example. So the plan here is to start with a word problem, convert the words into a calculus problem, and it's a max-min problem, and solve it using first derivative test, second derivative test, our extensive knowledge of finding extrema for functions. To get the ball rolling, consider this application. We'll have a step-by-step procedure, and we're basically following it in this as well. But first, let's just run through an example, a relatively easy example, to illustrate what we're up against. The question is, show that among all rectangles with an 8-meter perimeter, the one with largest area is a square. Okay, so they've given us the perimeter, and they've told us we're dealing with a rectangle. They talk about largest area, so there's the maximization part. Okay, so first, we'll draw a picture and label the things that we don't know. We don't know the width or the height of this rectangle, so let's label those X and Y respectively. W and H would be reasonable as well for width and height. The idea is, you might even want to think of this as if the perimeter was like a loop of string, and we're trying to maximize the area inside. Well, we could put your fingers in that loop of string and stretch it really wide by making X large, but then Y has to be small if X is large. Conversely, we could make Y large and make it really have a large height, but then X would be small. And the area is based on X and Y. So if I make X really big, Y is going to have to be really small, and the area is going to be really small. If I make Y really big, then X will have to be really small, and the area will be small. So there should be some somewhere in between making X as big as we can and making Y as big as we can that'll yield a maximum area. The claim is when X equals Y, that is when we have a square, we'll have maximum area. Okay, well, they told us the perimeter is 8 meters. In our picture, the perimeter is X plus Y plus X plus Y. So it's 2X plus 2Y. So we must have 2X plus 2Y equals 8 meters. Dividing through by 2, say X plus Y equals 4 meters. Solving for Y, dropping the meters. When we're measuring distances, in this one we're talking meters. When we're measuring areas, we must be talking meters squared. Solving for Y, we get Y equals 4 minus X. Why we solve for Y, you'll see shortly. Okay, X and Y are distances, lengths. So we must have X between 0 and 4. X can't be bigger than 4 because we've got some perimeter that involves a parameter Y. If X is bigger than 4, then Y has to be negative. That's what we get from this equation here. So X is between 0 and 4, which makes sense, especially if you think of the loop of string story. If X were 0, what I've done is taken that loop of string, which amounts to the perimeter of the fence, and I've pulled it tight and maximized Y. Y would go up 4 meters and come back down 4 meters, and there wouldn't be anything left for width, X. When X equals 4, then we stretched it side to side, and now X runs 4 meters over and 4 meters back for a total perimeter of 8 meters, but Y is 0. So the physical description of the problem will oftentimes impose what the intervals in which these variables can lie, determine what those are. So in this case, since X and Y measure lengths, I'm allowing a length of 0. That's going to give minimum area in this case. But I'm allowing for lengths of 0. That's not nonsense. Negative lengths is nonsense. So we'll keep x between 0 and 4, including the endpoints. It's nice to have endpoints, as you know, when you're doing max-min problems. Now, in terms of x and y, the area of that rectangle is simply width times height, x times y. So as a function of x alone, we already know y in terms of x. That's why we found it previously. We can write the area simply as a function of x. It's x times y, but y equals 4 minus x. So here's the area as a function of x. The question they've asked then becomes, what's the maximum of a of x for x in the interval from 0 to 4? You need to practice these because they're tricky, and you've got to be able to turn the words into a calculus problem. If you can't take the words and get a calculus problem, and you can't show your knowledge of calculus. So there's what we get for the question, translated in terms of the picture we introduced and the x's and the y's that we introduced. That we did a few sections ago. We dealt with maxima of functions on closed and bounded intervals. The maxima occur, here's the question again, the maxima occur either at critical points or endpoints of those intervals. So here's a of x, say 4x minus x squared. Let's distribute so I don't have to use a product rule to differentiate. The derivative is 4 minus 2x, so there's a prime of x. So that equals 0 when x equals 2. So x equals 2 is a critical point. It's the only critical point. The derivative is never 0 anywhere else, and the derivative is always defined. So x equals 0 is the only critical point. By the techniques of section 4.1, really it's based on theorem 4.2, local extreme values, said the extreme value of a function on a closed and bounded interval occurs at critical points or endpoints. So we'll test the critical points and the endpoints. We'll plug in x equals 0 into the original function, 4x minus x squared, that'll give us 4, 0 minus 0 squared, parentheses when I've substituted, gives an area of 0. Yeah, that makes sense. Y would be 0 then. It's when we maximize the width, when we stretched it horizontally and ended up with no height. Y was 0. A of 2 gives 4 times 2 minus 2 squared. That's 8 minus 4, leaves us with 4. Units are meters squared, by the way, because we're calculating areas here. And we plug in a equals 4, we get 4 times 4 minus 4 squared. Again, substitution is in parentheses. This leading 4 isn't. Okay, that's the number 4 that's in the definition of the function. And we get 0 again. So the maximum is 4, it's meters squared because it's area, and occurs when x equals 2 meters. And by the way, y was 4 minus x. So when x is 2, y is 4 minus 2, y is also 2. So the maximum area is 4 square meters, and it occurs when x is 2 meters and y is 2 meters. They asked the question about something about a square. Okay, so the largest area rectangle in this story has width 2 meters, height 2 meters, so it's a square. Its width and height are the same, and that's what they ask us to deal with. So there is a max-min problem, and I got nothing really new to say other than the book gives a step-by-step procedure to work these kinds of problems, and we'll follow those. In fact, we followed these pretty much in what we just did. So the textbook states the following steps, which should be used in solving the problems of this section. We'll follow these steps. In fact, we just did. Step 1, read the problem. Duh, so no work to show on that one, but of course you read the question. Secondly, draw a picture and label the parts that may be important to the problem. Okay, the width and the height were important in the picture in the previous one. Thirdly, introduce variables, unknowns. Find relationships between the unknowns. We did that in the previous one. The unknowns we introduced, we'll usually do these 2 steps together. The unknowns we introduced were width and height, x and y. Did we find a relationship between x and y? We did. They told us what the perimeter was, and we used that to find a relationship between X and Y. So we follow these very step-by-steppy, and we will to try to make it as compartmentalized as we can. It's easier for you to remember it if we always work them the same way. You do these on a test, it's easier for you to get partial credit if you always go through the steps. So we can see where the steps went wrong if necessary. Fourthly, write an equation for the unknown quantity. It was area in the previous example. Use the relations from above, step 3, to express the unknown quantity as a function of one variable. Well, yeah, we wrote the area as a function of X in the previous example by eliminating the Y. That's the using the relations from step 3 stuff. So we eliminated the Y because we knew Y in terms of X. They got to give you information to find these relationships. Taking their words and finding these relationships, in my experience, students struggle with that. So we'll put some emphasis on that. Big time drawing pictures. Having pictures when meaningful is useful in finding relationships as well. So we'll have the quote unquote unknown quantity, the thing we're trying to maximize or minimize. Then we'll maximize or minimize it. We'll test critical points, we'll test endpoints. Might not always have endpoints though. It's okay, we could deal with concavity. We could use first derivative information to make sure the extrema we're finding are maxes and mins. We could use second derivative information. We might not need either of those, like in the previous example. If you got a closed and bounded interval, maybe 0 to 4 it was in that example, all you got to do is check the critical points and the endpoints. You don't have to mess with the increasing, decreasing information. If you don't have a closed and bounded interval, and some of these won't, we'll have to deal with that. So there's no endpoints to check, and we'll have to do something involving first or second derivatives. All right, yeah, first step goes without saying. Of course, you read the problem. When we draw a picture, we'll probably introduce the variables at that stage. In my experience, students struggle the most with finding the relationships between the unknowns. This was maybe a similar problem when we did related rates. In related rates, you had to find relationships between variables. There, you often used the Pythagorean theorem. That'll pop up in these as well. You used similar triangles. That may pop up here. That one I think is likely to play less of a role here. You may be just given information that allows you to find these relationships, like in that first example where you were told the perimeter. So let's illustrate it in progressively more complicated exercises. All right, so let's run through some of these. This may take a while because some of these are fairly lengthy. All right. The shortest fence, question number 8. This is fairly similar to the first example we did. A 216 square meter rectangular pea patch is to be enclosed by a fence and divided into 2 equal parts by another fence parallel to one of the sides. So in your mind, you're trying to draw a picture that elaborates on that. First off, they gave us the area this time. Last time they gave us the perimeter. Rectangle should catch your eye. The fact that they plant peas in this patch is neither here nor there. Enclosed by a fence and divided into 2 equal parts by another fence parallel to one of the sides. So they've taken a rectangle and they've cut it in half. If I draw the rectangle horizontally or vertically, then they've cut it horizontally or vertically. So that's the story so far. What dimensions for the outer rectangle will require the smallest total length of fence? How much fence will be needed? Smallest total length of fence. There's the max min. It's a minimization. It's a minimization of the amount of fencing. So we're minimizing fencing given the area of this rectangle and this added little part of, we'll put a fence through the middle of it. And also how much fence will be needed. Okay, so I read the problem. There's part 1. Parts 2 and 3, let's draw a picture. So they're taking a rectangle and they're partitioning it into 2 pieces. For some reason, they want a pea patch on one side of this fence and on the other side of that fence and of the same area. I don't think that ends up mattering. But they've cut the field in half. How do you know they didn't cut it horizontally? Fine. You'll be interchanging what I've labeled X and Y. But if you want to cut it horizontally, you'll get the exact same answer. If it mattered, they would have had to tell us. Okay, so we've got, say, a rectangle of width X and height Y. How much fencing have we used? Well, that'd be the perimeter, like we had previously, plus this extra barrier that's put in the middle. So we'll have X plus Y plus X plus Y plus Y again. So the amount of fencing will be 2X plus 3Y. They told us the area of the field is 216 square meters. With the labels, the variables, the unknowns we've introduced, X and Y, the area of the field, the rectangle, is X times Y. So X times Y must equal 216 meters squared, by the way. Let's solve for X or Y. If you have no preferences, let's solve for Y in terms of X, and we'll do everything in terms of X. So we'll solve for Y and eliminate Y in an upcoming formula. But here's a picture, here's some variables, and here's a relationship between those variables. I want to rewrite as Y equals 216 divided by X. Divide both sides of this by X. Drop the units for a little while. Okay, so you need to believe these words create this picture and this relationship. What's next? The quantity of interest, which was the length of the fencing. So next we need to find the amount of fencing. I kind of already gave that away. The amount of fencing in terms of X and Y is 2X plus 3Y. Let's look back at the picture. Yeah, X at the bottom and X at the top, Y on the left, Y in the middle, Y on the right. So 3 Y's and 2 X's worth of fencing. So that's the amount of fencing in terms of the X's and the Y's. All right, and in part 4, they also wanted us to write that as a function of a single variable. We got it as a function of 2 variables, X and Y, but wait, we know what Y is in terms of X. Y was 216 divided by X. That was the last thing on the previous slide. So let's substitute that in for Y. We get 2X plus 3Y, 3 times 216 over Y, over X. 2X plus 3 times 216 is a 648 over X. How about we write that as X to the negative 1, because we're going to be differentiating shortly. Okay, so there's the quantity we're interested in as a function of X. Part 5, do the max-min. Also state the question. What's the question in terms of the symbols we've introduced? Question is, minimize F. Here's F as a function of X. What could X be? Well, I say X could be anything between 0 and infinity. Okay, there are no endpoints. It's the bad news on this one, so I can't check endpoints. Does that make sense? That X is between 0 and infinity. Let's go back to the picture. X, let's see, what is it? The field has an area of 216 square meters. Certainly X can't be 0. If X is 0, then there is no area. So we get a problem here, or if you like, we get a problem here. X can't be 0. X is a length, it can't be negative. So X would have to be greater than 0. Is there any upper bound on it? Well, I could make X huge. I could make it kilometers wide. That's going to take a bunch of fencing, and that's probably not where we're going to get minimum fencing, but it's not disallowed by the description of the problem. But if we make X really, really wide, then Y is going to be really, really small. But I could still enclose 216 square meters. You tell me how wide you're making x, I'll tell you what y has to be. All I got to do is divide your x into 216, x measured in meters, say. So there's no upper bound on x. It can be as big as you like. It can be as small as you like, as long as it's positive. So yeah, x can be anything positive. That is, x is an element of the interval 0 to infinity. Okay, that's a little bit of bad news. That means I can't just check critical points and endpoints. We'll have to throw some first or second derivative knowledge at it. Okay, well, let's find the critical points, and then we'll take care of it. Differentiate f. Here's f of x. So the derivative is 2 plus 648 negative x to the negative 2. Negative 648 divided by x squared. So here's the derivative, if you like, writing it in this form. It's easiest to differentiate these quotients when you can simply write them as powers of x. Of course, that's a lot easier. I still like dealing with quotients algebraically, though. So we get an expression of this form for the derivative. Let's get a common denominator. So take the 2 multiplied by x squared over x squared. So we can take this and try to factor it. We'll factor the 2 out. That leaves us with this. So what you got for critical points? Is 0 a critical point? Actually, the function is not even defined at 0. And 0 is not in the interval of interest. Yeah, the derivative is undefined at 0. For some technical reasons, it doesn't count as a critical point. It's not in the domain of the function. Critical points are in the domain of the function. That was the definition of critical point. But yeah, something goes wrong at x equals 0, but we're excluding 0. And something goes wrong when x squared minus 324 is 0. Sorry, nothing goes wrong. That's when the derivative is 0, but those give critical points. And the only critical points occur when x squared minus 324 equals 0. That is when x is plus or minus the square root of 324. That was sweet of them. That's a plus or minus 18. So at least it came out to nice integer values. We're looking at x between 0 and infinity, so the negative 18 is of no interest. It does make the derivative 0, but we're not dealing with a function that takes on negative x values. Feel like the domain is 0 to infinity. So it's x equals positive 18 meters, by the way, that is the only critical point in the interval 0 to infinity. So does that critical point correspond to a maximum or a minimum? Well, I hope it's a minimum because that's what we're looking for. How are you going to tell? We could apply the first derivative test. Let's do that. We can also apply the second derivative test and check the concavity. We'll do one of those before we're done. But this one I've worked in terms of using the first derivative test for local extrema, theorem 4.3.a in the notes. So we'll take the domain of the function 0 to infinity. We'll remove the critical point 18, produces the interval 0 to 18 and the interval 18 to infinity. Pick a number, any number from these intervals. How about 1 because it's an integer and it's little? How about 20 because it's relatively small? And I'm going to have to square it. So that's easier to square than 19. We're going to plug these test values into the derivative. How about this version of the derivative? Okay, so I've got an x squared here and here. So I'll plug the 1 in. We get a 1 squared here and here. It's in parentheses because it's been substituted. I've got a 2 out front, the minus 324. I do the arithmetic. This is negative 646. Anyhow, all that matters is it's negative. So the function is, first derivative test, decreasing throughout this interval 0 to 18. Plug 20 in. I get a 20 squared and a 20 squared. 20 squared is 400. Minus 324 is what, like 76? Yeah, 76. I think I may have dropped a factor of 2 in this. We should have 2 times 76. Yeah, I think I should have 2 times 76. A little computational boo-boo. I'll revise it in the notes. Positive, though, even with the correction, positive, and the function's increasing. So the function goes down, then it goes up, giving us a local minimum at 18 by the first derivative test. local minimum. Let's see, what all did they ask for? They want to know what are the dimensions of the outer rectangle that will require the smallest total length of fence and how much fence. Okay, so X is 18. They want to know Y as well. Only one critical point. This must be the absolute minimum. Yeah, we saw that from the first derivative test. We saw that was the only critical point. And so it must be not only a local minimum, but an absolute. When X equals 18, we have Y in terms of X. So we'll get 216 divided by X. When X is 18, that produces 12. So they gave us nice numbers ultimately. So the field must be 12 meters by 18 meters. That's the dimensions of the field. Let's see, the X parameter is 18, the Y parameter is 12 as labeled above, and that does matter. You used the Y value 3 times. Remember, we cut the field in half. So this was used 3 times. It makes sense that the Y value would be smaller than the X value because it was heavier in a sense. It weighed more. It took more fencing when Y was involved. It took 3 Ys and only 2 X's when we computed the fencing. So I'm not surprised we have a smaller Y value than we have an X value. Just some physical thoughts on that. And the smallest amount of fencing would be what we get by plugging that critical point 18 into the original function. It was, as given here, it was f of x was 2x plus 648 over x. It's from above, sorry. It's bounce back and forth with the slides. That's what we had. We plug in 18, we'll get 72 meters out for the total amount of fencing, and that's what they ask. So we followed the 5 steps. We drew a picture. We labeled it with unknowns. We found a relationship between those unknowns. In the first example, that relationship resulted from the perimeter. In this one, it resulted from the area, both times of a rectangle. We wrote the quantity of interest as a function of one variable, and we used that relationship that came from area to eliminate the y in the total amount of fencing, the quantity of interest. Then perform the max and min. If you've got a closed and bounded interval, good for you. All you have to check is critical points and endpoints. If you don't have endpoints, then it's a little more involved, and you may have to do some first derivative stuff, like we did. You have to make a chart and do the increasing, decreasing observations. Here's another one that's a little bit more involved. This is exercise 12. It says, find the volume of the largest right circular cone that can be inscribed in a sphere of radius 3. And they drew a picture for us. A totally standard calculus 1 max min problem. Okay, they gave us a picture. They've introduced variables for us. So thanks, Thomas's calculus. And in this right circular cone, they've labeled the radius of the cone as x. And for the, let's see, they've labeled this distance y. So the height of the cone will be y plus 3. And what they've introduced, they've also very suggestively introduced a right angle here. Here's the diameter, sorry, the radius of the sphere is 3. Here's another radius of the sphere is 3. But we've got a right triangle of hypotenuse 3. One side is length x, the other side is length y. Pythagorean theorem will give us a relationship between the x's and the y's. So having given us the picture, I think we got a fighting chance at working through this one. We'll follow the 5 steps. The first one was read the problem. We did that. The second one was draw a picture. Well, it gave us a picture. And they gave us some variables. All right, so let's use that picture and those variables to find a relationship between those variables. And they wanted the volume of the largest right circular cone. They want to maximize volume. So we'll have to write volume in terms of x and y. Ultimately in terms of only x or only y. We'll see which one's more convenient. Okay, so we'll use their picture. The height of the cone is labeled. Let's maybe call it h. Introduce some more variables, but ultimately we'll work in terms of x's or y's. But the height is y plus 3, as we observed, y plus 3. The radius of the cone, not the sphere, the radius of the cone, the base radius, is x, as labeled, r equals x, if you like. We got a right triangle here, so the Pythagorean theorem tells us we've got x squared plus y squared equals 3 squared. X squared plus y squared equals 3 squared. If you like, x squared is 9 minus y squared, and we could take the square root there. Let's hold off on that for a moment. But we've got a relationship between x and y. X and y are distances, so they got to be non-negative. So what physical constraints does that put, say, on y? We're going to end up doing this in terms of y. Y could be as small as 0. If y is 0, we've got this cone that sits in the top half of the sphere. It's physically meaningful in the picture for us to have a height of the cone be less than 3, but that's certainly not going to be a maximum volume cone. I doubt even having one that sits in the top half and would have its base sitting on the center of the sphere and run around the equator of the sphere, basically. But if y equals 0, that's what we'd have. So we've covered that. We've covered all reasonable values. One might argue you could take y to be between -3 and 3. You don't have a maximum volume then, but it does make sense to have a cone that has a height of less than 3, but they're little cones. So we're taking the y parameter to be a distance, so we need to take the y parameter, treating that as a distance, to be between 0 and 3. Then the volume of a cone, you'll have access to all these formulas, is 1/3 pi r squared h. Okay. R is the radius. We set it equal to x, so we'll get an x squared there. Remember the x squared expression up here? And h is the height, and we had the height as y plus 3. So we'll get a y plus 3 here. So here's the volume. In terms of x and y, we're going to want it as a function of x and y. So we need to eliminate the x or the y. Which will it be? If I wanted to eliminate the y, I'd have to solve for y in this relationship. That'd be taking some square roots. I could do it. Let's check other options though. If we want to solve for x squared, we did solve for x squared and no square roots. So let's let an eye towards the future drive our decisions now. So you want to eliminate x or y? You know what? I think I want to eliminate x this time. Actually, eliminate x squared. Because we got x squared in terms of y, right here, 9 minus y squared. So let's substitute that in for x squared. Then we get 1/3 pi, 9 minus y squared, times y plus 3. There's the volume as a function of y only. You want it as a function of x only? Good luck, because you're going to have square roots in there. You've got the knowledge to go through and deal with that. The algebra is going to be messy, though. So let's do it in terms of y. And that's why I discussed the range of y up here being between 0 and 3. We're going to have to differentiate this. How about we multiply it out? It's a product of two binomials. In multiplying out, we produce this. We still got the 1/3 pi out front. But here's what we get for the volume function. Now, what's the question? Largest volume. So the question is then, maximize this function over this interval from 0 to 3. You like that, don't you? It's a closed and bounded interval. We'll only have to check critical points and endpoints, so we won't be burdened with a table of increasing and decreasing information because we got a closed and bounded interval. So the question then is, find the maximum of that function we had on the previous slide for y between 0 and 3. We need the derivative, okay? Differentiate. Easy enough, it's a third-degree polynomial. We'll get -3y squared minus 6y plus 9. That's constants differentiated away. It still carries this 1/3 pi out front, of course. We factor 3 out, gets rid of the 1/3, leaving us with negative y squared, factor 3 out, minus 2y, factor 3 out, plus 3. So that produces this, and in fact, this can be factored into, say, negative y plus 1 times y plus 3. So here we've got the derivative factored. We're looking for critical points in the interval 0 to 3. 1 is a critical point. Negative 3 is a critical point as well, but it's not in this interval. Does it make sense that negative 3 is a critical point? Let's see, it doesn't count, but let's see, let's look back at the picture and see where that came from. So back to the previous slide. When y equals negative 3, if I tried to make sense out of that, we would have taken this cone and made the height, and the height would be 0 if I take y to be negative 3. So what you've got is a cone with height 0. It's going to have base radius 0, and it's going to have volume 0 as well. Well, that's an extremum because that's a minimum. So that's the reason negative 3 popped up. It's not just any number, that negative 3. So there's actually physical or geometric reasons for that arising. It's not of interest to us because we want critical points between 0 and 3. Okay, 1 is the only critical point between 0 and 3. So, section 4.1 material, extrema for a continuous function on a closed and bounded interval. Check the endpoints, 0 and 3, and check the critical point, 1. We plug in 0 to the original function. Here's the original function sitting up here. Plug the zeros in. They got parentheses around them where they were substituted. Produces 27 times 1/3 pi is 9 pi. Plug 1 in. Produces 32 over 3 pi. By the way, what's that? 10 and 2/3 pi. It's bigger than this. And when we plug 3 in, we get 0 out. Does that make physical sense? Let's go back to the picture one more time. This arithmetic is correct, so we get 0 out when y equals 3. But does that make sense? Yeah, when y equals 3, remember we're inscribing a cone inside this sphere. Well, if I make the height 6, there's not room for any base radius. The base radius would have to be 0. If y equals 3, x has to be 0. Well, that's another one where the volume is 0. Yeah, that came up because it's a minimum. And the minima will occur at endpoints or critical points as well. So what we found is actually a minimum here over that interval. So we choose the largest one. As we observed, this one is 10 and 2/3 pi, so it's the biggest of the 3. Must be the maximum. So the maximum volume is 32 pi over 3 cubic units. They didn't tell us what they're measuring the thing in, so I don't know. Cubic whatevers. That's the maximum volume. They didn't ask us this, but they often do. That occurs when y equals 1. And we can solve for x because we know x in terms of y does require a square root, and we get this x value. So if they ask us for the dimensions, they did in those fields that we've done so far. But if they ask us for the dimensions x and y, there's what they are. Easy enough to find once you found the point of interest, the maximum in this case. We follow the steps, same as always. Let's do another one. All right, the trough in this figure is made to be, is to be made to the dimensions shown. Only the angle theta can be varied. What value of theta will maximize the trough's volume? Okay, I've been teaching out of this book for a while. They've reworded this question. Originally, they said you have a sheet of metal 3 feet wide, and you fold up the sides to create a trough. The sheet of metal is 20 feet long. How do you maximize the volume of the trough? Well, same idea as what we have here. but you can see them evolving the words in the question to make it easier for you to convert those words into ultimately a function. They've given us a picture, so we're off to a good start. But the idea is, what could theta be to give us maximum volume, maximize the trough's volume, which is really equivalent to maximizing the cross-sectional area, but we'll deal with the volume hands-on. I drew this picture here. If we fold the sides up and call this little angle theta, if theta equals 0, we've got the sides vertical, and you've got a rectangular trough. If you took it any bigger than that, and you fold the sides in, of course, you're getting less volume. So I guess it's plausible that theta equals 0 could correspond to the maximum, but we'll take theta to have a lower bound of 0. That's meaningful. And upper bound, I want an upper bound. How about pi halves? At theta equals pi halves, we wouldn't have bended up any and in the volume 0. So I bet you that's a minimum. So we'll restrict this theta value to be between 0 and pi. All right, they got a picture to get us started. Here it is. Specifically, theta is the little angle here. That's what they indicated. They meant to indicate at least. And we've got 1 foot along the sides and the bottom. Let's look at this little triangle here. So let's take this triangle and pull it out of the picture. It's a right triangle. We've got 1 for a hypotenuse. We've got theta for this angle. What's that mean the adjacent should be? Should be cosine theta. Take the ratio of adjacent over hypotenuse, we get cosine theta over 1. And we should get cosine theta. Take the opposite over hypotenuse, we get sine theta over 1. Yeah, it should be sine theta. So here's the lengths of those other sides, and that has a relationship to the dimensions of the trough. But we're finding those dimensions in terms of this angle theta. Everything's got to be done in terms of theta. So we use trig functions to find those distances. As we observe, we'll take theta to be between 0 and pi halves. Of course, the 0, excuse me, some technical difficulties here in my printer. I'll be back. Okay. Sorry, technical difficulties. Technology. Okay, so we'll take theta to be between 0 and pi halves. Then we've definitely got a right triangle. We're taking theta to be an acute angle. You might have some concerns about including the endpoints, but I want to include the endpoints. So all I'll have to do is test endpoints and critical points. Okay, we want the volume of the trough, carrying that little picture over. We can think of the cross-section of the trough as 2 of these triangles, one on the right, one on the left, plus this little rectangle. The triangles have, if you like, base sine theta, height cosine theta. The rectangle has base 1. Remember the rules about 1 by 1 by 1. And the height is cosine theta. So break it into 3 pieces. I know how to find the area of a rectangle, base 1 times height cosine theta. I know how to find the area of a triangle, 1/2 base times height. Treat the base as sine theta, the height is cosine theta, or vice versa. And we get 1/2 sine theta times cosine theta. So the cross section of the trough then is 2 of the triangles of area 1/2 sine theta cosine theta, plus base times height of the rectangle. What we're actually getting out here is square feet, it's cross sectional area. The 2 and the 1/2 cancel, giving us sine theta cosine theta plus cosine theta square feet. The trough in the picture was 20 feet long, so we'll add in that 3rd dimension, and then we get 20 times that cross-sectional area. That'll give us cubic feet, and that'll give us volume. So there's the volume as a function of theta. The question is, maximize volume for theta between 0 and pi halves. There's the volume, simply as a function of theta. critical points and endpoints. You got to be able to turn the given words into the calculus question. Once you got that done, the calculus part is going to be straightforward because you're good at differentiating. The algebra might get a little tedious, but the calculus part, I think that's the easiest part. Setting it up is tricky, and sometimes the algebra is tricky after you differentiate. Let's see what happens this time. Okay, we got a product of functions here. So when we differentiate, we'll have to take the 20 out front. We'll have the derivative of the first, derivative of sine is cosine, times the second, which is cosine, plus the first, sine, times the derivative of the second, derivative of cosine is negative sine. We'll differentiate cosine over here and also get a negative sign. Let's see, that's a cosine squared minus sine squared minus sine, the 20 out front. How about this? Let's take cosine squared and write it as 1 minus sine squared. When you have even powers of sines and cosines in the same formula, you can swap them. You can swap cosine squareds for sine squareds and sine squareds for cosine squareds. Let's get rid of the cosine squared, write it as 1 minus sine squared. You probably did this in pre-calculus 2 when you dealt with trig functions. And then that gives us nothing but sines here. So I'll treat the unknown as sine and try to factor it. So we get a 1 minus sine squared. Here's another minus sine. So we'll have, let's see, 1 minus sine theta minus 2 sine squared theta. Yeah, 1 minus sine theta minus 2 sine squared theta. And this factors. Just think of sine theta as like a little x. You've got a 1 minus x minus 2x squared. Well, that can be factored. So we get 1 plus sine theta times 1 minus 2 sine theta. FOIL this, and indeed it produces that. So we got the derivative, and we got the derivative factored. Next slide, we'll look for critical points. We'll have the critical points by setting these two factors equal to 0. I'm only interested in critical points in this interval. There may be many more, but we'll find the critical points in this interval, plug those in, and plug those endpoints in. Okay. V prime of theta, we left off with this expression. So there's the derivative factored. So critical points, this is always defined. The only thing that could go on is this be 0. That occurs when 1 plus sine theta is 0, which means sine theta is -1, or when this 1 minus 2 sine theta is 0, and that occurs when sine theta is 1/2. Well, there ain't any thetas in the interval 0 to pi has, for which sine theta equals -1. These are acute angles. All the trig functions are, where they're defined, they're all positive in that first quadrant, so none of this. Sine theta equals 1/2. There is a solution to that in 0 to pi halves, depending on your knowledge of special angles here. The sine of pi 6 is 1/2. So theta equals pi 6 is a critical point, and it's the only critical point in that interval. Excellent. All we have to do is check the endpoints, 0 and pi halves, and the critical point, pi 6. So we'll plug those into the original function. The original function was v of theta. It was 20 sine theta cosine theta plus cosine theta, bracket it off. So we'll substitute 0 in. Okay, sine of 0 is 0, that term's gone. Cosine of 0 is 1, so we pick up a 20. It's cubic feet, by the way. We'll plug in pi 6, kind of expect that to be the one we're looking for. We plug pi 6 in, sines and cosines of pi 6 involve square root of 3 over 2 and 1/2. So use that special angle, evaluate the trig function, simplify. This is what you get. So I'll leave it to you to read through that. The arithmetic is correct. The trig's correct. So we get this out, which for the record's about, from a calculator, it's about 25.98 what cubic feet. It's bigger than what we had up here. And then we plug pi halves in. Remember what that means physically. That means you folded those edges up none. We plug pi halves in, we get 0 out for the volume, as expected. So this matches the physical idea that we had. So which is the biggest? This one, 5 square root of 3 plus 10 on the square root of 3. Let's take the exact value because we can. And that occurs when theta equals pi 6. So the maximum volume is as given here in cubic feet and occurs when theta equals pi 6 radians. Okay, let's cut this video and we'll start another one. We got several more of these to go. Some of them are a little more complicated in the ones that follow. So we'll do some complicated ones in the next video. Thank you for your support. I'll see you shortly and we'll work more applied optimization problems. It'll be awesome.